so today is a third chapter in my outline, and it will consist, in fact, deriving from the original water wave problem model equations. And today we will derive Boussinesq and KdV. Of course, this morning you heard the lecture of Robin, who explained to us how from the original equation one derives KdV with the appropriate scaling. So of course I will have the same scaling, but I will proceed differently in the sense that my starting point will be the Hamiltonian system, and I will introduce into the Hamiltonian our appropriate scalings and go along with this transformation to ultimately get this Boussinesq and KdV. And I would like also to mention another approach that I should have discussed yesterday, but I forgot. I would like to mention the recent work of Dario Bambuzzi, and thank you to Vincent, who reminded me that so Bambuzzi, he derives again the high order KdV equations using the methods of normal forms. With so it is you have to put that in parallel to the two rigorous papers that I mentioned. The first of Craig of '85, the other one of Schneider and Wayne that proposed the wave decomposing in two waves, one to the right, one to the left, satisfying KdV. And Bambuzzi, he goes further. He, in fact, derives two waves, one of fifth order. So it's a higher order term in the KdV. And he uses normal form. So it's again another approach. But normal form is very close to the Hamiltonian structure, uses the Hamiltonian structure. Okay, so in order to do that, we will have to learn how to do transformation. So we'll spend some time trying to understand what means calculus. I call it calculus of transformation. Essentially, I start from the Hamiltonian system. I introduce transformation. How does this Hamiltonian system? How is this Hamiltonian system transformed after this transformation? Okay, so that will be our. So we will learn some rules how to make these changes, and after that, we will have essentially all the tools to get Boussinesq and KdV. Okay, and just for those of you, the younger one who have less experience with Hamiltonian system, I will just start with simple observations, just examples of Hamiltonian system. So maybe you all know them, but just to make you familiar with it. So one, I choose nonlinear Klein-Gordon. So nonlinear Klein-Gordon is the equation utt minus uxx, or I can even put Laplacian u. You can put it like this. We put v. Okay, that's minus v3. That's Klein-Gordon. It's a Hamiltonian system. How do you see it? Well, you take two variables. One is v, and the other one is p dtv. And this system writes vp okay, maybe I'll just so Well, you can probably see immediately that if I defined H, the Hamiltonian of V, comma P, of that's the usual energy. I have to dx. If H is the total energy of the non-linear Klein-Gordon, you can recast the equation into 0, 1. Okay, and this is a symplectic matrix, so symplectic matrix operator. Sometimes it's an operator. Here it's a simple matrix, so identity. That's the first example. You probably are familiar with it. Another example, even more familiar, maybe it's nonlinear Schrödinger. E ut plus Laplacian u plus lambda u. And here, of course, u is complex. Is complex, and you can write again a Hamiltonian 1/2 gradient u square plus lambda minus lambda. I like to put 2 sigma here. Okay, so that's the Hamiltonian, the familiar Hamiltonian, and you write the equation dt u bar. So here the matrix is 0 minus I 0. And the final example that you probably know also is KdV. So the goal is to show you different symplectic operators. KdV xxx plus minus u p, for example, Hamiltonian being 1/2 and in the case of KdV, the equation is, it's the conflict between u and v, and then it's dtu equals dx, right? So j dh du. Okay, and what is g? J is minus dx. Okay, so in this case the g. So that's just a little warm up to Hamiltonian problems. And now I would like to go to this question of calculus of transformations. And first, just one example. I mean, that's not example. One result in a kind of formal way for a general transformation, and then we'll apply this recipe to the problem that interests us, in particular in including scalings. And of course, as we introduce this transformation, we will have to see how the Hamiltonian transform also. So there will be several steps. Okay, so assume that we have a two-phase space, x1 and x2. And in x1, we have a Hamiltonian, h1, which is associated to H1, we associate an evolution equation, a Hamiltonian equation of the form dTV equals G1. So G1 is a symplectic operator. It could be in either of these problems. dV, okay? Okay, H1 is a Hamiltonian. And I would like now I introduce a transformation of the variables. So tau is going to be a transformation from x1 to x2 to phase space, and it will I will denote it V gives W equals tau of V. Okay. So you can imagine later tau of V will be, for example, multiplication of V by epsilon. That's an easy case. And I would like to, so by this transformation, I would like to understand how this equation becomes, how this transformation modify the Hamilton system. Or in other words, what is the equation satisfied by W? So first of all, we will have we will have H1 of V H1 of V. H1 it will be, we will write as a function of, okay, so we rewrite H1 in terms of W. So since it's not the same formula, I called it H2. And H2 of W. And we would like to see how this evolution equation changes. So I put G1, yes. Okay, so it's not too complicated. I write dTW. So I would like to write an equation for W, evolution equation. I write, so it's dV, the Jacobian of the transformation, times dTV, okay, the Jacobian of the transformation tau, and dTV is d, so this I copy, dTV is, it's the gradient, it's G1, gradient, respect to V of H1 of V. So in later, our V will be a taxi, right? Later. But for now, it's just a general V. And now I would like to express this gradient H1V, which is also gradient. So gradient respect to V of H2 of W. I would like to express it in terms of W, right? In terms of W. So we can check. So I will do the calculation. What is gradient? Gradient respect to V of H2 of tau of V, right? And I want to understand how it acts on a little element, an element of the scalar product, L2 scalar product. This is D. Okay, I'll just do it for this one, and then I think you are familiar now with this calculation. That's the dd epsilon, derivative with respect to epsilon, of H2, and now of what? Of tau, of V plus, oh, epsilon, yeah, so epsilon is okay. Epsilon, okay. No, not yet. Okay. You with me? And this, I can rewrite it again as derivative respect to W, derivative respect to W of H2 derivative respect to W of H2 and dV, the Jacobian applied to dV, Jacobian of tau okay, this way, and I use I put this this Jacobian by the how do you say adjoint. So, well, this is just a little heavy to write, but we just do it once. dW. So in any case, that tells me that this quantity, I can write it as the adjoint of the Jacobian multiplied by the gradient of H as a function of W. So what have we obtained? We have obtained that dTW equals, so now I copy this J1, and what is that? It's exactly dV tau star H2. Okay. So in this calculation, the original equation in terms of V has been replaced by dt, oops, there is a gradient. I'm not consistent with my notation, unfortunately. Sometimes I put gradient, sometimes I put a D like that, sometimes but they're all the same. Okay, so that's our new equation. Now, if it happens that X2 has a symplectic structure that I call G2, so this is G2, G2. If it happens that so let me not call it G2, let me call it J. If it happens that X2 has a symplectic structure and with a matrix G2, G2, and if it happens, if J equals G2, symplectic structure on X2, if it happens the two J are the same, then we say that tau is canonical, is a canonical transformation. Okay, and if it's not a canon, if it's not exactly, well, we will have to modify it by this transformation. Okay, so that's the formulas that we will use systematically for different transformation. So we'll have a list of the transformation that will be appropriate for this calculation. So, examples. So, the example 1, imagine, so we have V is ataxy, right? It's our problem, the water wave, and I associate to V W equals alpha V, alpha eta, beta xi. So later it will be epsilon, for example. And then what happens to the, so the Hamiltonian in terms of V will be transformed to a new Hamiltonian equation. And so that's, in this case, it's pretty simple. dv tau is just the matrix alpha, beta, 0, 0. And the new, the G2, or the J, will be alpha, beta, J. So you have to compute this. You have to compute the other one. Maybe I should write it for that time. This is the same. So, okay, that's an easy one. And the new J is alpha, beta, G1. So the new equation is, in terms of W, it will be dTW alpha, beta, J1 gradient V. All right, so usually when you have a term like this, you would absorb it in time, with the time, through the time. You change the time and you recover the same symplectic structure. Now, another example, maybe a little bit less trivial, but not too difficult, is that, so that's the scaling of the dependent variable, right, of dependent variables. Scaling of independent variable. Well, you remember that we're going to be in a setting of long waves. So long waves, what does that mean? It means that if I have a function v of x, I would like to see it as a function of capital X, where capital X is epsilon x. Right? That's meaning. Okay, so let's rewrite it a little bit better. To associate to the function v, the function w of x equals v of x over epsilon. X over epsilon. Right? I just get rid of the big letters, so it's remain. So this is exactly tau of v. Tau of v. Yeah. Of x. Okay. And you may again want to calculate the Jacobian. The Jacobian of the function tau respect to v, well, applied to an element of L2, for example. So you do this traditional calculation. It's DDS of DDS at s equals 0 of tau of v plus sh. Okay? And what do you find? You find that this is equal to h over x over epsilon. And when you do the adjoint applied to a little h, you find. So you do the calculation, I let you do it, epsilon v1 of epsilon x, epsilon h of epsilon x. And when you compose the two, so we have to go here. Yes, we have to go here, that the new symplectic operator, we need to calculate that, and we find we find that dv tau j1 dv tau star equals epsilon j1 j. Okay, so that's one of the important calculations, which means that the new system, if we apply this transformation, will be dtw so h2 is the same as h1, but written in the w variable. Okay, you comfortable with that? That's yes. Which h? Oh, the little h is I'm looking how this Jacobian acts on an element. So it's this element, little delta v. Oh yes, of course. Tell me. You should have told me earlier. Okay, I'll do. Thank you. Yeah. Okay, so these are the two scaling that will come all the time, and other transformation will be important. Can calculate. I think I had this like this, but maybe I'm mistaken. So let's see. Alpha, beta. Maybe I'm wrong. I think it's just the product. Okay, so I start with this one. 0, that gives me 0. Maybe there's a minus. Or okay. Maybe there is a minus somewhere. No, it's correct. Oof. No, because I remembered, by memory that that was correct. If I did not remember, I would not be able to do it. These things you have to learn to know by memory. Okay. Otherwise, you always make a mistake. Okay. So another transform. But thank you for asking. It's really nice that you were asking. Okay. Another important transformation is that we're going to do, because in the course of derivation of Boussinesq and then KdV, is that from the variable, so another transformation C, from the variable eta and xi, we will go to eta and u, which is a derivative of xi. So it's similar. It's not exactly, but it is the derivation, the derivative of the velocity potential tangentially to the curve, right? Okay. So what is so that's then the tau. So what is the Jacobian of tau? The Jacobian of the transformation is so eta does not change, and xi involved gives us a derivative. Okay, and if I calculate d tau v, dv tau, star. Oh, is it big enough now? 0, so it's 1, 0. Change the sign because you have to go, it's integration. All right, so what happens to our new j is going to be 0, well, 1, 0, 0 dx, 0, 1, minus 1, 0. And if you calculate this, you get 0, 0, 0, minus dx, minus dx. Okay? So, because we will use it later, I write again the new Hamiltonian. It's dt eta u equals 0 minus dx 0 the new Hamiltonian because that will be useful later, because when you go from the water wave to Boussinesq, in fact, these are the variables. Okay, and another important transformation. So this is from from the original variable to the surface elevation and the velocity. And the other one that I think is useful that we do is what we call characteristic. So that's the third example, the fourth example, going to characteristic coordinates. So it's a little bit like in hyperbolic systems, you go to Riemann invariants, so to see waves, to see somehow, to diagonalize the system. Okay, so let me take the example that will come up. Assume that H, well, it's our H here. It is simply so this will be the linear part of our Hamiltonian later. So I'll just take the linear part to simplify, to see how this is modified. So this is our new H, the one that I'm using here, and the small h will be in the future. It will be, you know, when we have the waterways, we have the G is the gravity, and h is an average average depth. Okay, thank you. Okay, and I would like to. So what is the equation? It's nice to write the equation. The equation is dt eta plus h dxu equals 0, and okay, and it's convenient. Well, you want to diagonalize it so that this equation will become dtr. So I tell you the answer, and then we'll find the transformation. It will be dtr equals square root of gh dxr equals 0. Also, that makes you think of KdV already, right? Going to the right, and dst minus KdV going to the left. Okay, and to do this, so we have the Jacobian here. We have the matrix J here. I need to tell you what is the transformation. The transformation is this one. So we will see it often. So the new H, so the H is going to be reduced to, let me see the correct coefficient. Yeah, the new H is going to be H, well, the notation is not so good, but it's just temporary. We're not keeping all this tilde anywhere. So you see, it's very nice and simple. The Hamiltonian is the equations are diagonalized, and the Hamiltonian is simple. And what we can say, so I have to tell you what is R and S finally. So it's a little bit complicated, but since this expression come often, at some point you get used to it. So it's the fourth, so I'm going to write a little bit bigger because it's big expressions. And the good thing, we will not have to repeat it later. So essentially it's eta plus u and eta minus u, but with the appropriate coefficients. So this 4 means square root power 1/4, right? And this 4 is a real 4. And S is the same, but with minus. Okay, so that will be important when we go. And finally, I should write the system. And here we have, so you do the transformation. It's just very simple here. Don't need to write it. Okay, what is it? It's minus c dx minus c. Is it plus c dx? And c is square root of gh. Okay. Okay, so we have gone through all the examples that we need to do the derivation and the transformation. There is one thing we need to do also, is in our water wave problem, we have this Dirichlet-Neumann operator, which is not easy to manipulate. So we have to see how, when we introduce this parameter of small amplitude, long wave, how does this Hamiltonian, because we will be in small amplitude regime, so we will need to do expansion. So I would like to spend a little time to discuss the effect of this scaling transformation on the Hamiltonian. Yeah? Well, I said I'm just taking this as an example. Later, this is going to be the quadratic part of the Hamiltonian. But yes, this is just when we work out the problem, the Hamiltonian is not going to be this, but it will have an expansion. In the same way that the Dirichlet-Neumann has an expansion, there will be an expansion of the Hamiltonian, and this first term with the quadratic, which corresponds to a linear problem. Quadratic Hamiltonian corresponds to a linear system. It will be exactly that. So that invites us to introduce this. Thank you. Oh, yeah? Yeah? Or maybe there's no C here then. There's no C. Yeah, okay, thank you. Thank you. Yeah. Thank you. Okay, and what, so now I would like to add one element is so the second part of this. So we had this calculus of transformation. How do they influence? How they modify the equation essentially? How they modify the symplectic structure and how they modify the H. Now we have one more thing to look at. We're going to return to the spatial scaling. The spatial scaling was this one. The one, is it still here? Yes. The one that want to look at functions as function on long waves. Okay. And how does this spatial scaling effect? So effect of spatial scaling on multiple on Fourier multiplier. On Fourier multiplier. Now, why Fourier multipliers? It's because in anticipation to what we're going to do, we will have the Dirichlet-Neumann, and the Dirichlet-Neumann in the regime of small amplitude, we will use its expansion in eta, because eta will going to be epsilon eta. So we're going to use this expansion, and this expansion of Dirichlet-Neumann are composed of Fourier multipliers and multiplication by function. So in particular, we will need, for example, we will have a theorem or a result about the action of scaling on a Fourier multiplier. So let me state the result, and I will explain it. We will not prove it, but we will at least try to understand what it means. So we have assume M of D. We introduced it the other day. M of D is a Fourier multiplier. Fourier multiplier. Do I need to repeat what it is? We okay? Everybody's okay? Yeah. And so remember that D is a symbol 1 over I dx. So it has. We assume that it is of order M, for example. What does that mean? It means that if I take the derivative respect to M k, so here k plays the role of a wave number. So dkj. So the k derivative respect to M, seeing as a function of little k, constant 1 plus k square, and here, so it's for order M, meaning that, well, this we will need later, but we can. Yeah. To the power m minus j over 2. Okay. So we want to understand, we would like to find an expansion on m of d acting on a function u that is a function of epsilon x. Okay, so that's what we will have. And there is a formula that tells us that it's almost, because if you have, let me explain before I write the formula, if you have a function u, which is a function of epsilon x, and you differentiate it with respect to x, well, it's epsilon, the derivative of u, with respect to the big variable, right? So this is essentially meaning that each time we see a d, a derivative with respect to x, in fact it comes with an epsilon. So that's how the expansion in epsilon comes up. So it's sigma over j equals 0. We can do it at the order we want. It's like doing a Taylor expansion. Here, 1 over I dx. dx. X is going to be the variable epsilon x, j u of x, plus a reminder. And one can prove the following estimate. So I expanded this the action of m on a function of on a long wave as in this way with a reminder, and there is the theorem says that you can control the reminder. The reminder in let's say in HS, in HP, let's say, is multiplied, so epsilon n plus 1. It's the next term, right? I went up to n, so it's epsilon u. And there is a relation between Q and P. Well, it's a little bit complicated. Sigma. So I don't know what sigma. Well, it doesn't really matter, but and sigma. So we are in dimension 1, so I think it's just 1/2. Okay. So that will be a systematic formula, but maybe it looks a little bit mysterious. So let me show you with some examples. So excuse me? Well, often, for example, if you take the operator m of d equal hyperbolic tangent hd, right? So it's a zero order operator, but you can expand it as much as you want. No, put it. Right. So a proof of this theorem is in one of my papers with Walter at that time. It was Craig, me, Chance, and me. That was 97. But it is not complicated. Just go back to the definition of Fourier multiplier and expand. So we're not going to use it in this complicated form. So let's take an example. So certainly we will need to we have G0. Remember G0 d hyperbolic tangent HD. Okay, and we will have to apply G to a function u of epsilon x. So what shall we do? We're going to say, well, it's G Let's put d of d. It's very intuitive. It's like differentiate with respect to x. Little x is like differentiate with respect to a big x, where x and this. So we will write. So what is G0 of this? It's epsilon. There is already an epsilon. There is a dx. Well, we're going to don't touch that. We can't go further. And then touch epsilon h. Okay, and apply to u. So essentially, we expand this operator attach, like Taylor expansion, and we will find. So we have epsilon. Is an h, and then the next one, is it plus or minus? The tanche is a plus or minus? Okay, that will be, that's how we will deal with Fourier multipliers with spatial scaling. The change of variable of spatial scaling acting on a for Fourier multiplier.
Probably minus.
Oh, probably minus. Thank you. Don't know why I have plus here. Okay, so now we have all these elements. We're going to put them all together and introduce. Start from the water waves, introduce the scaling like we had it with Robin for Boussinesq, and we will systematically have this transformation and the corresponding evolution equation. Okay. So we have all the elements to go to do this derivation of the Boussinesq system. So you remember that for the Boussinesq system we have to introduce small parameters, as we had with Robin notations. It was epsilon measures the amplitude over the average depth, right? And we're going to assume delta, which is the depth over the wavelength. Okay. Length, that's depth. And this is amplitude. And we are interested in this special case where epsilon squared is going to be delta. That's the what's called the KdV scaling. All right. So in this spirit, we're going to introduce new variables, and especially so x is going to be epsilon x. So we call that long wave. Sometimes it's a little bit confusing that it's a long wave, but you have to think that if I want capital X to be 1, it means that little x must be very long, right? So the physical variable is long wave, and this is just 1. And so in this new variable, I will assume that eta, the elevation, is epsilon square eta of x, and I put a little tilde because it's a new variable, and associated to again, and in C is epsilon. And you may ask, why is it that we have epsilon square and epsilon? Well, it's because the true variable for Boussinesq and for KdV are eta and u, the derivative. And the derivative involves another epsilon, so there are two epsilon square. Okay, and that's all. We have H. And well, there is one little difficulty we have that comes always with the Dirichlet-Neumann operator, is that it's a complicated operator, just a derivative. It's not just a derivative. So when we implement in this Hamiltonian the change of variables to express everything in terms of eta tilde and expand in epsilon, we'll need also, because epsilon, eta will become epsilon square eta tilde, so we need an expansion of the Dirichlet-Neumann in powers of the elevation. Okay, and this goes back to what we learned yesterday, which was the expansion of eta the expansion of the Dirichlet-Neumann in powers of the elevation. So G of eta, we're going to write G0 and we will not need more than G1. And I remind you, G0 is already there. That's G0 is the easy one, it's the Fourier multiplier. And G1 is homogeneous of degree 1. Okay. And we put all this into now associated to this expansion of G, we have an expansion of H also, right? So it's convenient to rewrite H so that's the first, that's what we call the quadratic Hamiltonian. Quadratic Hamiltonian is associated to the linear problem plus Xi G1 of eta Xi plus plus plus. Okay. And now we have to replace our X's by this, our eta by that, the dx, little x, the little dx by capital X, well, the epsilon dx, and at the same time, yes, and order everything in powers of epsilon. Okay, so if you want to have a little break, and then when we return, we will do that, and we just fall on Boussinesq. Okay, so I wrote epsilon square equal delta, but in fact the delta goes here. The square goes here. And we will check carefully when we do the expansion that it comes. But so here is our scalings. We assume that eta is very small in amplitude and depend on long wave. And Xi is small again and depends on long wave. And we're going to replace, we're going to put all this epsilon inside the H, right? So I need to cope with this. So it's convenient to rewrite G of eta in terms of, let's say, G tilde of eta tilde in the in this formula. So what do we see? Applied to a function, G of eta. Okay, I'll leave it like this. So this G0 is d tanh G0, but now, since it's going to be applied to a long wave, I'm going to replace G0 by epsilon dx. And I copy this epsilon h dx. And that will be enough for now. And the other one, plus. So I am reading G1. So when I read G1, I have an epsilon coming from D. So I have epsilon square, and this eta gives me 4. Okay, so we have dx eta tilde dx, and then minus. So this one I'm not going to write it, but it doesn't really count, because if we recount, we see so G0 is already epsilon square, right? So epsilon square, so that makes it epsilon 6, right? So I'm not going to write it. Okay. So these two terms are of the same order, epsilon 4, epsilon 4. So let's write now the h. So you see it's not very complicated. So h tilde of xi tilde eta tilde equals 1/2 integral over r. So we have xi. Xi gives me an epsilon, and this one gives me another epsilon. So there are at least 2 epsilon square, and then multiplied by so epsilon. There will be epsilon 4. And then, well, there will be some correction. Yeah, you are right. Because this is a quadratic Hamiltonian. Plus, and the next term is epsilon square now, because it's epsilon 6, and then minus h3 plus c tilde. So this one was which one? It was this one. And now I write this. And although I don't write parentheses, so just to make sure we agree, it's the derivative respect to the variable, the long wave. What do I write? Eta I put the parentheses so there is no confusion. and dx over epsilon. Okay. So plus O of epsilon 5, because we're losing one epsilon here. All right. You okay? And now, so we have to keep track of the transformation. We made transformation on little x. We made the transformation of the transformation of the spatial variable, of the amplitude, of the dependent variables. And now I'm going to make another transformation by having u tilde equal dx xc. So I write dx because I want a velocity, I want something real. So it's 1 over I. Oh, it's not a 1. I upstairs. Okay. So now I copy. And you know, at some point we get a little lazy in changing notation. So I can put 2 tilde, but it becomes a little ugly. So at the end, you prefer to keep H, and it change the name. But that's a detail. Okay, so what do we have now? We have H3 integral. So here, H, so you can integrate by part, and dx has the I, so it gives us u square plus, so that's why, if you remember, that was, Mathieu, you asked me. Plus epsilon 2 okay, epsilon 2. Okay, this one. And this one you can again integrate by part. So, but that makes 2 derivatives on xi, so 1 derivative on u. So it will become, and you have to be careful with the signs. The signs should be minus, and they all compensate. And here again, there is something you should have complained. No complaint. This goes here, integration by part, that's a u. Eta tilde u tilde. Okay, so that's the Hamiltonian. And now we would like to, so we have eta xi. Okay, that's a Hamiltonian in new variable. We have eta tilde xi tilde. Okay. Then we have u tilde, eta tilde. Okay. So this transformation leads to a modification. What for the symplectic matrix? What happens if you remember it multiplied by alpha beta? So this is epsilon square, epsilon. It was alpha beta. It was 1 over. Thank you. So epsilon minus 3. Then we have the scaling that gives us another epsilon. Okay, and then the matrix. You remember that going from eta xi to eta u, introduce the matrix minus dx. Okay. Oops, not in the right place. It has to be symplectic, so it has to be. So finally, our new Hamiltonian system, after this transformation, becomes dt eta u. Okay. Hmm?
I'm a little concerned about this O of epsilon to the 5 that we have as header.
It is not a proof, it's a calculation, it's a asymptotic calculation.
But it's the same order as the second term inside of
No?
just epsilon cubed times epsilon squared. In the second
You sure?
I think maybe it should be epsilon to the 7 because the order.
Yes, it should be higher. Yeah, it should be higher, thank you. Yeah. But it's a reminder that I don't estimate, right? I don't calculate its size, right? I just say it's of order epsilon. Yeah. Yeah, thank you. Okay, so what happens here equals so tell me how many epsilon I should write. Epsilon minus 2 or minus 1? Minus 1. 3 minus 1. Minus 2. Minus 2. But we have to count, right? So we have epsilon 3. So that gives, I'm a little bit confused now. So tell me how many epsilon I should have. Epsilon. Just one. The eta. And now O of what? We have maybe epsilon 3, something. Okay. So what are the equations? dt eta tilde, and this is Boussinesq. We are done. We have Boussinesq. I mean, we have one Boussinesq. Sorry? Mm-hmm. Hamiltonian system is what? Oh, tilde, yes. But yes, at some point I will going to lose this tilde. Okay, what is it? This H. Okay, so we have to differentiate respect to u. That's easy. To eta, that's easy. We can differentiate respect to u. It's again easy. You just integrate by parts, etc. Respect to eta. So all that we can calculate the derivative respect to eta, the derivative respect to u, and we find that. So I give you the final result. Because this calculation, the derivative differentiating the Hamiltonian respect to u or eta is simple. Okay, and this is called, in fact, it's not called the Boussinesq system. Now we're going to drop the tilde. Because we don't need to remember what they are. So you see the first term, the one that do not get epsilon, are the linear term. Right? We're going to absorb it with the time. This is usually what we do. Okay. Yeah? Hmm. So epsilon 3, epsilon minus 3, these two goes away, and epsilon remain. That's the epsilon. No, this epsilon minus 3 comes from these. And this second epsilon comes from this. Okay? Thank you. Okay, and then, so, all right. So, first of all, when you have an epsilon like that, you like to absorb it into the time. Okay, so you like to say, well, epsilon t equals t. We know that we are in a situation where we are at least long time. Not very long time, long time. So you can, if you allow me, I will drop this epsilon and replace t by dt. Okay, and this is the Boussinesq system. No, well, this is one Boussinesq system. And in fact, it's called, so first of all, let's see. If you drop the epsilon, you are just led with to t dt eta plus dx h du equals 0, and dtu plus g dx eta. That's a wave equation, right? So that's why we discussed later. So later we're going to have R and S, like we did. So this system is called the Kaup-Zaks model. And it was derived by Kaup, by Kaup in 76. So this system is Hamiltonian by construction. Okay, it's Hamiltonian by construction. It is integrable by inverse scattering. It has explicit solutions, but it has some problem of ill-posedness. And that's a fact there. So there are other, that's not the model that Boussinesq, so it's not the Boussinesq that Robin introduced this morning. The Boussinesq introduced by Boussinesq, the real Boussinesq, is a little bit different. So I'm just going to write to you because it's interesting. The original Boussinesq from 1877. So it is dt eta plus h. So I don't write the epsilon. You can, don't write the epsilon square. We know they are. Oh, no, I write them anyway. HU. Equals 0. That's the original Boussinesq. It is well posed. That's the original Boussinesq. It is well posed. It is not Hamiltonian. And some people like to, you see, because in a sense, at lowest order, you could say dt eta is exactly dxu. So since this term dt square eta is multiplied by epsilon square, at the order of this approximation, you could replace this. People have replaced that by minus dx square u. And that's another Boussinesque, which has even better properties in terms of ill-posedness. So so then we're not going to get too far, but there is a kind of ABCD Boussinesque. And that was introduced by Bonnat, Chen, and So. Essentially saying, well, I can put any coefficient I want so that because of this approximation, they don't count. And depending, so maybe I'm not going to write it because it's a longer, but all possible combination. And depending on this ABCD, you have solitary waves, you have ill-posedness, you have well-posedness. And so this is the family of Boussinesque. Now, so Boussinesque is a little bit not perfect, but it is useful because it takes into account both direction. From Boussinesque, we can easily get to KdV. Okay, if you have no question, I continue. I will erase.
Yes, I have one question. I'm a little bit disappointed because we work with n-dimensional quantities and we still have h, which is related to epsilon and delta.
No, H is H.
Because we have the ratio h over lambda, which is.
I already took it into account. When I had when we had, for example, hyperbolic tangent, epsilon HD, we had this. I did not touch H. I mean, you could, from the beginning, you could have H equals -1 if you like, or +1, but I did not. H is fixed. G is fixed, H is fixed. I don't touch this constant. I have taken into account already by scaling the variable x, capital X. We can discuss it later. Okay, so yes, so if we're going to derive KdV now. From Boussinesque to KdV. Okay. So you remember these characteristic coordinates? You agree? When you remember the coordinates R and S that I introduced earlier? Well, they are appropriate to transform this linear part into the two waves moving to the right and to the left. And so maybe you just remember them, right? I don't need to write it again. Or I write it. That was those of the previous hour. Okay, so now if we change these variables to Boussinesque to these characteristic variables, we know already how this where is it? How this symplectic matrix will be, because we calculated it earlier. So I'm going to write. If you don't mind, I don't put tilde. I'll just put H of R and S equals. So epsilon cube. Why do I have epsilon cube? I don't remember why I have epsilon cube. Oh no, I should have just epsilon, right? Epsilon. And then I have the correction. So what is it? Where is the Hamiltonian? Well, it's here. When I see u or eta, I replace it by, well, something like r eta equals r plus s multiplied by something, and u is equal r minus s multiplied by something, right? By this constant. I just solve it. Solve back. So the remaining term are a little complicated, but not too much, plus epsilon. So I think it continues into this equation. Maybe I need more space. So I repeat, H okay, so these are the quadratic. This is the quadratic part. The cubic part. So we have this coefficient. This constant a little bit annoying, but we have to write them. That's eta square. That's u. H1 cube. Okay. And that's a linear term, but it's high order. It contains a lot of derivatives. So I started from, I took the system that I did. I took I took the Kaub-Sachs system, Kaub-Sachs model, right? These were discussions, but this is my starting point. That I replaced eta and u by r and s. Okay. In the Hamiltonian, finally, the equations are so I got tired of writing the form, the constants. I just put C1, C2, and you can write it for yourself. So you recover you see the. Oops. So these are coupled KdV. So that's the two waves going to the right and left, and these are the correction. So this needs a number of comments. So it's not exactly the same coefficients. It's r square. Okay. It's epsilon cube. So I'm going to put yes. Okay, you can. Yeah, it's okay. So it's a square. Okay. All right. So these are the two KdVs. They are complicated. Now, if you want to reduce the calculation to 1 kdV, it means that you have to decide that S is very small, that you are in a configuration that you can neglect the wave going to the left, and then you obtain exactly everything where S is there disappears, and you obtain kdV. So then you obtain dt. And then, but if you want a nice kdV, you have to modify a little bit the reference frame, the frame of reference. Okay, so if you want to stay with kdV, you first change the reference. That makes it a new variable. T. Okay, and then you absorb the epsilon square in the time. That makes it a very small time, a very long time, a very long time. So you see, for the papers of Schneider-Wayne or the paper of Bambuzzi, who prove rigorously the approximation of the KdV, of the water waves by KdV, by 2 KdV, they have to, to really show the separation, which is a very difficult problem. Okay, so if you are interested, you could go into this analysis. That could be very good. All right, so we have just a little bit of time, and I'm going to if you have no question, I will start slowly the next chapter. Yeah. Well, you know, in this setting we have two essentially two coupled KdV, right? It's more complicated than KdV, but we have two waves, and one effort has been to say, when you want to prove, for example, that it's a good approximation, you may prepare your initial conditions so that the wave going to the left will be negligible. So that's only, words. If you need to do the proof, it's another story. But the idea is to say, well, I neglect the wave on the left and I concentrate on the right. But you see, it's a very systematic derivation. Yes? You're asking why? So that was the Boussinesq original. But what I'm saying is that if you look at this equation, essentially at leading order, dxu is like minus dtu. Okay, because this is of small order. And so here we have epsilon square multiplied by two derivatives. So because we have thrown away all the terms of higher order, I could replace dt, two derivative respect to eta. I read it here, two derivative respect to eta plus h, so I differentiate once. So I'm not going to say that. I say, yes, two derivative. No, it's the x. Yes, because if you look at this part, and I can replace it by dttu minus gh dxx or dt eta u equals 0, right? Just this part. That's the wave equation. So plus epsilon, plus order of epsilon square. So because we are already at epsilon square, and we have neglected all the terms, I say, well, this can be as well dx square. So that's the philosophy of people working with Boussinesq. But I learned that Jean-Claude Sau is writing a big book on Boussinesq. So with not only this one, but the higher in dimension, because Boussinesq, there are Boussinesq equations in 2 dimensions. So it's quite rich. Okay. So the next step in this program is moving to, ultimately, I would like to show you how the derivation from the water wave problem to the nonlinear Schrödinger equation, because that's the two big derivation, KdV and NLS. But prior to this, because I'm using those tools to do this derivation, I would like to introduce you to Birkhoff normal forms. So Birkhoff normal forms are not related at this moment to derivation of asymptotic equations, but they are tools developed for Hamiltonian system. And the general idea is that we're going to make some transformation. This transformation will be canonical, so we will never lose the Hamiltonian character. There will be change of variables. And this change of variable will have the effect that we can eliminate many terms. We can eliminate terms that are called non-essential, nonlinear terms that are non-essential. But some terms we can never eliminate. They are called the resonant term. So if one performs this transformation very carefully, you might end to a situation where you have maybe transform your equation of second order to its equation in third order, etc. But all this is done in the assumption that you have small small conditions, because the heart of the problem is that you have an expansion of the Hamiltonian in small for small conditions, for small functions. So the Hamiltonian, because since we have, so we will be in a situation where eta and xi are small. So we perturb near the flat water at rest. And often so at lowest order, we have the linear problem, linear system. dt. So what is it? 0, G0 minus G0. And the linear problem, of course, we know to solve well. So in the terminology of dynamical system, the point eta xi equals 0, 0 is called an elliptic problem, elliptic point. Because if that refers to the fact that if you diagonalize this matrix, it has eigenfunctions that are purely imaginary. So that's the terminology. But since we'll be considering small data, small eta and xi, we will rewrite the Hamiltonian. There will be since we have since eta and xi are small, in particular eta is small, we have an expansion of the Dirichlet-Neumann operator. And associated to this expansion of the Dirichlet-Neumann operator, we will have an expansion of the Hamiltonian. And by construction, the first term is quadratic, the second is cubic, etc., etc. And this transformation will eliminate, if we can, the non-essential nonlinearity from the Hamiltonian. Okay, so that's the general idea, and one of the very beautiful results that was obtained in '94 by two independent teams. There was Zakharov and Dyachenko on one hand, and Craig and Wolfok, was proved that on one they were considered a 2D problem with deep water. They proved that you can eliminate all these H3 terms, and for H4 you can eliminate many terms, and those who remain are what's called integrable, because it depends only on the action. So I think the calculation is not too hard, and because it's very unique by its simplicity, I think I would like to do this calculation, show you how these Birkhoff normal forms are constructed, because they're quite explicit. And after that, I will use this formalism to derive NLS, but that's another story. That will be later. And these things are usually done in a periodic setting. So I will keep the periodic setting. Periodic setting means that we'll assume that in the x direction, the functions are depending. So these functions x and eta are periodic in the x variable. Okay? So they are studied, they are considered on the torus. So that's the program for tomorrow. Okay?